We've been spending a lot of time thinking about multiplicative inverses of integers mod n, and now we're going to find a more systematic way of finding those multiplicative inverses by looking at an extension of the Euclidean algorithm. So we're first going to review what multiplicative inverses mod n are. We're going to review what the Euclidean algorithm does, and then we're going to use the Euclidean algorithm to find multiplicative inverses mod n. All right, so remember, if you have integers a and n such that a mod n is not equal to 0, we say that x is a multiplicative inverse of a mod n if when you multiply a and x together and then take that number mod n, you get the number 1. And we found out that if you have integers a and n, then this happens, being able to have a multiplicative inverse happens, mod n, precisely when the GCD of a and n is 1. In other words, a and n are relatively prime. They don't share any significant common factors. So for instance, if we're looking at 7 mod 15, we can look at 13 times 7, that is 91. If we look at 91 mod 15, that gives you 1, and that tells us that 13 is the multiplicative inverse of 7 mod 15. In general, if you have a times x mod n equal to 1, which is what we're looking for if we have a number a and we're looking for a number x that's its multiplicative inverse, if we want to look at that using the definition of congruence, because remember, that means that 1 is congruent to ax mod n, that means that 1 is equal to ax plus some multiple of n times y, for some integer y. So that equation is what we're really looking for in finding a multiplicative inverse for the number a. All right, so let's see what happens when we find the GCD of n and a using the Euclidean algorithm. Remember, in general, when the numbers are super big, it's really hard to do it just by factoring. So we do it using the division algorithm, using quotients and remainders. So we divide a into n, giving us n is equal to a times the quotient q plus the remainder r. And then what happens is the GCD of n and a is equal to the GCD of a and r. And what that means usually is that as we repeat this process, the numbers that we're taking the GCD of keep getting smaller and smaller. So for instance, back in the old days when we found the GCD of 8 and 19, we would divide 8 into 19, giving us 19 equals 8 times 2 plus 3. Then we'd look at 8 and 3. Those are our next two because those have the same GCD. We'd have 8 is equal to 3 times 2 plus 2. That gives us 3 and 2 as our next numbers. Notice they're getting smaller. And that gives us 3 equals 2 times 1 plus 1 equals, and so that tells us that the GCD is equal to 1. At the very end, we got the 1. That's as low as our GCD can go. So, a couple of observations I want to make. First of all, in terms of multiplicative inverse, we want 1 is equal to a times x plus n times y. We want to find an x and a y that make that true. So that tells us that the x is our multiplicative inverse. But for the Euclidean algorithm, notice that at our very last equation, we eventually get a remainder of 1. So 1 shows up in both of those equations in a significant way. The question you might ask is, can we use the Euclidean algorithm to find x and y? So that would give us our x as our multiplicative inverse. Well, let's see if we can. So we want to find the multiplicative inverse of 8 mod 19, trying to use the Euclidean algorithm. So this is what we're looking for. 1 is equal to 8x plus 19y. 1 is one of the remainders that we get from the Euclidean algorithm. Let's see if we can write all the remainders from the Euclidean algorithm in the form 8x plus 19y and eventually get ourselves down to 1. Seems like we're doing more work, but what's going to happen is we're going to use the earlier remainders to help us with the later remainders. And you'll see how. So remember, our first quotient and remainder was 19 equals 8 times 2 plus 3. And that means our first remainder is 3. And then our next one was 8 equals 3 times 2 plus 2. And our last one was 3 equals 2 times 1 plus 1. And then remember, our remainders are 3. So we want to write 3 as a multiple of 8 plus a multiple of 19. Then 2. That means we want to write 2 as a multiple of 8 plus a multiple of 19. And then finally 1. So for 3, let's see. First thing we want to do is subtract that 8 times 2 from both sides so that we're solving for 3. Remember, we want to write 3 as a multiple of 19 plus a multiple of 8. And just doing that, we pretty much got it, right? So we got 8 times negative 2 That's our second term. I'll move it to the front. Plus 19 times 1. And we'll play the same game with 8 equals 3 times 2 plus 2. If we subtract 3 times 2 from both sides, notice that 3 appears both in that equation above, on the first line, and in the equation that we just had. So I'm going to take that 3 above, which is, remember, is 8 times negative 2 plus 19 times 1, and replace that in the 3 below. So that gives us 8 minus, all I took the 3 is and replaced it with 8 times negative 2 plus 19 times 1. And now I'm going to combine all the 8s together, combine all the 19s together to get us what we want. So the first thing I'm going to do is distribute that darn negative. That can be a real pain. So when we do that, the negative 2 becomes a 2, so we get 8 times 2. And the 1 becomes negative 1, so we get 19 times negative 1. Then notice that 2 on the right, I'm going to distribute that, use the distributive property. So when I multiply that by the first one, 8 times 2 becomes 8 times 4. It gets multiplied by 2. And then the negative 1 becomes negative 2. In the second one, we get 19 times negative 2. So now we're almost there. If you look at the left, we have 1 8 and then 4 8s. If we combine them, that's 5 8s, 8 times 5, plus 19 times negative 2. 2 remainders down, 1 to go, and we're pretty much going to do it the same way as we did before. One little twist, but we'll be okay. So remember, these are our first 2 remainders. 3 is equal to 8 times negative 2 plus 19 times 1. And then 2 is equal to 8 times 5 plus 19 times negative 2. And our last quotient remainder equation was 3 equals 2 times 1 plus 1. Now remember, we're solving for 1, the remainder on the right. So that gives us 1 is equal to 3 minus 2 times 1. And now notice that we have a 3 and a 2 in that equation, but we also have an expression for 3 and an expression for 2 in those first 2 lines. So we're going to replace those in just like we did before. It's going to be a big old mess. So that's what we replace our 3 with, 8 times negative 2 plus 19 times 1. And then we also replace our 2 with 8 times 5 plus 19 times negative 2. And now we play the same game as before. We're going to distribute that negative through that second set of parentheses. So that 5 becomes a negative 5. The negative 2 becomes a 2. We combine our 8s. There's negative 7 of them because we have negative 2 8s on the left. And then a couple spaces over, negative 5 8s. That gives us negative 7 altogether. And then we got 1 19. And then 2 19s gives us 3 19s. And that gives us exactly what we want. We have 8 times negative 7 plus 19 times 3 is equal to 1. Which tells us that, remember, we were looking for the multiplicative inverse of 8 mod 19. Our multiplicative inverse is negative 7. We want to do that with positive numbers, so we take negative 7 mod 19. That gives us 12. Whew. All right. Let's do one more example just to make sure that we're comfortable with this process. So now we're going to find the inverse of 7 mod 26. This one's a little bit more applicable to us because we're going to find, we like finding inverses mod 26 when we do our encryption and decryption. All right, so we're going to start with our division. We're going to look for quotients and remainders. So our first quotient remainder pair are 3 and 5. And then we use 7, we use 7 and 5 for our next pair. 7 is equal to 5 times 1 plus 2. And then 5 and 2 are our last pair. 5 equals 2 times 2 plus 1. That is our Euclidean algorithm to find the GCD of 7 and 26. Fortunately, that GCD gives us 1. Yay. But now we're going to find our remainders as multiples of 26 plus multiples of 7. So the first one's always pretty easy. You just take everything except for the remainder, except for that 5, move it to the other side. You get 5 is equal to 26 minus 7 times 3. And then we're already there because we get 26 times 1 plus 7 times negative 3, exactly what we wanted. Right, a multiple of 26 plus a multiple of 7. For the next one, we're going to solve for that 2. We get 7 minus 5 times 1. Notice that we have an expression for 5. 5 is equal to 26 times 1 plus 7 times negative 3. That's what we got in that first equation. Now we're going to distribute that darn negative, right? So that 26 times 1 becomes 26 times negative 1. 7 times negative 3 becomes 7 times positive 3. And then the 26s are already combined. We're going to combine those 7s. We get a 7 on the left, 3 more on the right. That gives us 7 times 4. Finally, we're going to solve for 1 in that third equation. 1 is equal to 5 minus 2 times 2. Notice that we have an expression for 5 that we got in the very first equation. That was 26 times 1 plus 7 times negative 3. We also have an expression for 2. We only have to deal with one of those 2's, right? We don't need to deal with both of them. We have an expression for 2 that was equal to 26 times negative 1 plus 7 times 4. We'll plug in that in. And then it's just a matter of simplifying, combining our 26's, combining our 7's. So first thing I'm going to do is I'm going to multiply that negative 2 through the parentheses. So or the positive 2, right? We're multiplying that by 2. So that 26 times negative 1, we double that, but multiply it by 2 to get 26 times negative 2. For the 7 times 4, that's going to become 7 times 8. Then we're going to distribute that negative sign. The 26 times negative 2 becomes 26 times positive 2. The 7 times positive 8 becomes 7 times negative 8. And then we combine our 26's. We have 26 times 1 plus 26 times 2. That gives us 26 times 3. We combine our 7's. We got negative 3 of those on the left, negative 8 of those on the right. We get 7 times negative 11. So that gives us the equation 1 is equal to 26 times 3 plus 7 times negative 11. Remember, we were trying to find the multiplicative inverse of 7 mod 26. We notice that 7 times negative 11 gives us 1. So that's going to be, negative 11 is going to be our multiplicative inverse. If we want to give a positive number version of that, we'll take that number mod 26. That gives us 15. And just in case you're a little nervous that 15 is the wrong answer, we're going to go ahead and check that. When we take 15 times 7, we get 105. 105 mod 26 is equal to 1. And miracle of miracles, that tells us that, our inverse of 7 mod 26 is 15. All right, so now let's see if you can try this out on some of the problems in the PDF file included with this video. The name of the file is Extended Euclidean Algorithm.